Lens center of gravity location. In this lecture, we want to talk about the center of the gravity of each individual lens. As I mentioned before, each lens can be decomposed by three main elements or main category. For example, you can see this is a some sort of complicated lens that we have two spherical surfaces, we have a truncated cone in the middle, and we have a cylindrical disc. This lens can be decomposed by two spherical segments that for simplicity we just call it cap, and one truncated cone, which is this red part, we call it cone, and one right circular cylinder that we call it disc. So this lens can be decomposed by the main elements. And for each element, for example, for cap, we have some sort of equation that we can find the weight and the center of the gravity. So for this cap, the diameter is d, the sagittal depth, which is the distance from here to the plano-convex segment of the lens, is s, and x is the center of the gravity of this part, which is from the plano-convex side to the center of the gravity. So this is very important. We should be aware that the center of the gravity of the cap is always calculated from the plano-convex, but we usually start from right hand side or left hand side. We should consider this fact that the center of the gravity is from the plano-convex of plano surface of the lens. So for S, which is the sagittal depth, we have this equation, which only have R, which is a known parameter. D is also as a known parameter. So the sagittal depth can be calculated using this equation. And the weight of the cap by using the volume times the density of the lens can be calculated by this equation, which we have the density of the lens by different kind of glass is different. And the center of the gravity, which is the x of cap in this for this lens, because it's a cap side of the lens, is equal to s times 4r minus s divided by 4 times 3r minus s. So that's the center of the gravity of this cap, which is a part of the big lens. So now for truncated cone, that we have the diameter d1 here, d2 here, and the thickness is L. We can find by using this equation weight of the cone. Again, we have the density of this part following by this equation, and x of the cone, which is the center of the gravity of this cone, from surface d1 is equal to this equation. So we use this equation to find the center of the gravity from this specific side, from d1 side, or it can be from d2 side, but in this equation we should change the d1 to d2. Now for a disk, it's pretty simple because disk is completely symmetric. The center of the gravity is L, which is the thickness of the disk, divided by 2. And for the weight of the disk, it's a circular object like a cylinder. We have the density is followed by this equation. So disk is pretty simple. Now for a lens that comprising n parts, it can be any kind of element. The center of the gravity of each lens that included a lot of elements is followed by the same equation. This is the equation that we use for center of the gravity of all objects. So for cap 1, we have x prime. You remember for the previous equation we put x, but x prime is the distance from any reference. For example, if you start from here, x prime is this distance. We should be very careful because, as I mentioned for the previous equation that I mentioned, x is from the flat surface. So x prime is the center of the gravity of the cap. X prime cone is the center of the gravity from, for example, this reference to here, and we have the weight of the cone. X prime of the disk is the center of the gravity from this reference to here, and we have the weight of the disk. And x prime of the cap is from here to there, and we have weight of the cap. So center of the gravity of the whole length that can be somewhere here is equal to x prime times the weight of each length divided by the total weight of the length. So for the total weight of the length, we can say it's equal to sigma of wi, because we just add them up together. So now let's look at an example. For example, in this scenario, we have a very complicated lens. The two cemented lens, one of them is a plano-convex lens, that this side is flat, this side is convex, and the density of the plano-convex is 0.091, and the material is NBK7. And for the plano-concave part, which is cemented to the plano-convex part, the density is 0.173, and the material is SF4. So we have D1, 1.8 inches, 29.97 millimeter. This is D1. This is D2. This is R1. We have R2. We have the total thickness. We have the L1, which is the thickness of this disc. And we have L2, which is the thickness of this disc. So first we start with cap 1. S1 is equal to this equation. Based on this equation that I mentioned before, we have R and we have D. We put it there, we find S1. And based on S1 and R1, we can calculate weight of cap 1, which we use this equation. So very easy, weight of cap 1 is known. For the disk, we have L1, weight of the disk, followed by the equation that I mentioned, or this equation. We can find weight of disk 1. L2 is known, D2 is known also, so weight of disk 2 is also known. For cap 2, which is this negative length, sagittal depth, again we use this equation to find sagittal depth. R2 is known, and we can find cap 2, weight of the cap 2. So we have all weights, and we have all weights is known. Now we need to find, based on those weights that we have, we need to find the center of the gravity of the whole element. So we start with cap 1. This is the equation that we have for cap 1, x cap 1. As I mentioned before, x cap 1 is from here to here, from the plano-convex side. But right now we want to calculate it from here to there. So x cap followed by this equation, x prime, we actually calculated we have s, which is 0.0966, minus this distance, which is x cap 1, that we calculate 0.82 or 0.03 in inches. So we subtract these two numbers to find the cap 1, x cap 1. So in order to make it clear, let me draw. So based on the equation that I mentioned before, x cap can be somewhere here. So this one is x cap. And the sagittal depth is from here to here. This is S. And right now, because this is our reference, this surface is our reference, we want to calculate this distance, that we call it x prime cap 1. So x prime cap 1 is equal to S, which is this value, minus x cap, that we have an equation for that. This is the equation that we use for x cap. That is for this value. So by actually let me erase everything. So by this equation, we can easily calculate x prime cap 1, which is from here to there. So multiplication of wi xi cap 1 is equal to this. We have this number, and for x of the disk, this one is very simple. X of disk is half of the thickness, which is 0.05. And again, for this equation, because as I always mention, we start from here, that's our reference. So we have S plus X of disk, which is S1 plus X of disk 1, which is equal to this equation. Now again, let me make it a little bit more clear. This distance is S1, and the X of disk 1, which is this part, the center of the gravity is somewhere in the middle, which is L1 over 2. So from here to this center, from here to here, this distance is equal to S plus X of disk 1. So by putting numbers, plugging number into this equation, we can find all the numbers. And for again the same equation for x2, half of the distance, not x prime of disk 2. Again, we don't need to write it down. We start from s1 plus l1 plus half of this distance, which we put into this equation, and w3, I mean for the third element, x of this gap is, we plug in number to that equation and we get to this. And then finally we have x of cap 2, and cap 2, s1 l2 l2 x cap 2, because as I always mention, x cap 2 is started from the plano-convex, and the last surface, the plano-convex side, is attached to L2, so it's a straight distance. And by putting into this equation, the total x, or the center of the gravity of lens, is 7.399 millimeter from left hand side of the lens. You can prove for yourself that either you start from the right hand side or left hand side or any reference, you get to the same number. Thank you very much, and here are the references that I used for this part. Thank you.